Okay, so my first question to you is, what is the name of this function? Of course. What is the name of this function?
Absolute value.
Right. So what do you think the name of such a function would be? And this is an example, and here's another one. Let's say g of x equals 1/3 everything to the x.
Exponential.
Yes, because the variable is the exponent. And this is the base. This is the base. In this case, it's 1/3. And this is the power or exponent in both cases. So when we start talking about the exponential function, one of the two functions in this chapter with wide applications in real-life situation, we're going to have to discuss two things. We are going to have to discuss about the base, and we also have to talk about the exponent. Here's the next question I have for you. 1 raised to the 4th, 0 raised to the 3rd, and -3 raised to the 2nd power. Do these exist? Yes, so 1 to the 4th would be 1. 0 to the 3rd will be, and -3 squared will be 9. However, these are not allowed for exponential functions.
Because x is not the exponent.
Nope, not because of that. So I will say base. The base is denoted by a or b, doesn't matter. The base, a, cannot be 0, 1, or negative. And the reason is not clear at the beginning, but I will tell you what is the reason. The reason is this function you will see in a few minutes is a one-to-one function. What do we know about the one-to-one function? A one-to-one function has an inverse. Awesome. That is also a function, and it's also one-to-one. Correct. So when we are going to graph this function in a few minutes, you will see it's one-to-one. It has an inverse function. The inverse function will not exist. We will not be able to create the inverse function if the base of the exponential is negative, 0 or 1. So then what can the base be? So the base can be two things. First thing, greater than 1, not 1. The second possibility is a number, a tiny positive number between 0 and 1, not 0, and not negative.
Like 0.5?
Exactly, or 1/2, or 1/3 in my example. Yes. Okay? So yes, we can determine all these, but they are not allowed in the exponential function. The base of 1, the base of 0, and the base of negative number is not allowed in the exponential function. So now I would like to look at these two because, like with x squared or negative x squared, two different shapes, opening upward having a minimum or opening downward and having a maximum, this function has two shapes. One, when the base is greater than 1, it will look totally differently, like x squared and negative x squared, totally differently. And when the base is tiny positive. So we have to look at both. Okay, so let's start with 2 to the x. So we talked about the base. Now it's time to talk about the exponent, because I want to graph the function f of x equals 2 to the x. When I'm asked to graph a function, what do I have to do first? What do I have to determine first for any function?
The y-intercept?
Yes, I have to know what the function is. But what is the first step afterwards? The other than Tom. Domain. Always. I don't know where to put numbers in if I don't know the domain, right? That's the first thing. Okay, so then I start my chart. And now let's think. Remember what is the issue with domain? I don't have to do anything for this function. I just have to think. Okay, can I put here 2?
Yes.
Yes, because 2 squared is
4.
Can I put 0 in here?
Yes.
2 raised to 0 is
One.
1. Awesome. Can I put -5 in here?
Yes.
It's going to be 1 over 2 to the 5th. So then, can we identify the domain of any exponential function? We plugged in, exactly, we plugged in everything. We plugged in positive, we plugged in 0, we plugged in negative, right? So
The range is limited.
this will join the category of friendly functions. Say it again.
Friendly function?
Yes, I don't have to worry about the domain.
If it's only
Okay.
fractions
I like that, yeah.
Right?
No worries.
No worries, like polynomial.
Right.
I don't have to worry about anything
As long
when
as
it
I'm
comes to
rational,
It's not like rational, it's not like radical. Exactly. Very good. So I'm going to pick a couple of x values. Let's say -2, -1, 0, 1, and 2. So please tell me what happens when I replace x by -2. What is the y value that I get?
1/4.
Correct. Do you all agree? Yes? Okay, very good. So this is indeed 1/4. Can we plug in -1 in the function here, in the exponent?
Yes, we can.
Okay.
And this time, I think I'll abstain from answering.
Anyone? When I plug in -1, what do we get?
1.
Very good. And when I plug in 0?
1,
Good. When I plug in 1?
2,
And when I plug in 2?
4.
Good. We have not determined the end behavior for any function the way I'm going to do it here. So don't really apply it to other functions. It works here though. I'm going this way. 1, 2, 4, 16, 32, 64, 128. Where am I going?
To infinity.
Very good. Now I'm going the other way. A pi divided by 2. You get a lot. Pi divided by 4.
0.
Pi divided. Okay, so what does this mean? And this we know from the previous chapter. When x approaches -infinity and the function values approach a number, what does this mean?
Is an asymptote?
Yes, it is a horizontal asymptote, but look, we've never seen this before. Only at what end? So only at -infinity. So y equals 0, horizontal asymptote at -infinity only. We had rational functions with horizontal asymptotes on the same horizontal asymptote on both sides. We have never had something like this. A horizontal asymptote here and a blow up here. Okay, so let's graph the function. So we have, and then you'll see how many different properties this function has. Okay, so when I graph a function with asymptotes, what do I have to graph first?
The asymptotes.
Correct. Although this is an overkill, because this is y equals 0. And please give me the first order pair that I need to plot.
-2 1/4.
The next one.
-1 1/2.
And then 0, 1. And then 1, 2. And so on and so forth. And this is the function 2 to the x. It has the highest possible growth. An polynomial function will not go that fast to infinity. Okay? Good. What can we say about this function? A lot. What is its domain?
Real numbers.
Correct. So number 1, domain, -infinity to infinity. Number 2, range.
All positive numbers.
So how do I write it?
Parenthesis 0, infinity.
Good. Number 3, is this function increasing or decreasing on all its domain?
It's definitely increasing.
Right. Here's my hand right here. right? So the function is increasing all the time. Number 4, x-intercept.
Technically, once you reach negative infinity of the x, you reach 0.
But can you reach negative?
You can't.
Okay, so what do I say for x-intercept?
No.
None. Number 5, y-intercept. All these are very important properties because we're going to look at transformations in a minute.
0, 1.
Very good, awesome.
Y-intercept for exponential functions is always going to be 0, 1, right? As long as it doesn't violate.
Very good. So the answer is yes, if it's a pure exponential function.
Not if it's a decimal.
If it
As long as
has
it's not modified.
modified meaning using transformations
Yes.
on it. Correct. Yes. So this is the function. If I need to shift it to the left, I'll shift it to the left, or I shift it to the right. But once I have to shift it down or up, it will move the horizontal asymptote. Or I should say the horizontal asymptote will move with the graph.
Okay.
So we're going to have examples in a minute.
The same rules for graphing quadratic functions?
Yes,
Okay,
absolutely the
same
same. Absolutely the same
Okay,
rules.
so
Yes, when
horizontal
we talk about transformations, they will stay the same no matter which function we are looking at.
for anything. So
Right, absolutely. Good question. Okay, 6. Horizontal asymptote.
Zero.
Y equals 0 at negative infinity. Good. 7. Is it 1-to-1?
Yeah.
By the
Horizontal line test.
good. 8. Does it have an inverse?
Yeah.
Of course. If it's 1-to-1, it has an inverse. Very good. Okay. I would like to, I don't know anything about the inverse function, but I'd like to graph it here together with 2 to the x. So, can anyone give us a couple of ordered pairs that I need to use in order to graph the inverse function?
1, 0.
Very good. 1, 0.
2, 1.
2, 1.
4, 2.
4, 2. I also need something here between 0 and 1.
I think this is actually a radical function. The inverse.
1/2 negative 1. So a radical function doesn't have a vertical asymptote.
Oh, right. It just stops.
Right. So this is f inverse. Now, if you remember, the graph of f and f inverse are symmetric with respect to the line. Which line?
Y equals X.
Indeed, because we reversed the coordinates with respect to this line. Good. So I think we are ready now for this problem. So f of x is negative 3 to x plus 1 and plus 4. We're asked to graph this function using transformations. Of course, I have to start with the base function. Can anyone tell us which base function I used to create f of x? Did I use the absolute value? Did I use the square root? Did I use
Exponential.
exponential? Which one?
Wait. Base cannot be negative. Oh, wait. If it's in parentheses. So then, yes.
So, which one? Which is the base function here?
3 to the x.
That's it. This is the exponential function I used to create f of x. Good. Now I would like to, in order of operations, present the first step, the first transformation on 3 to the x. I don't want you to think that I'm talking about the base. I'm talking about the base function or the original function, right? So I'm not talking about this. I'm talking about this when I say base function. Okay,
Function
so
about the x-axis.
say it again.
Reflected about the x.
That's not the correct order.
Translation.
Yes, so I have 3 raised to x plus 1. Where does this go?
Up 1.
No, depending on what I'm changing.
Oh, down. No, wait. Left 1.
Exactly.
Right.
Left 1. Number 2 is a transformation on number 1. Nope, there is none.
Right, so reflecting.
Yes, negative 3 raised to x plus 1 reflect with respect to the x-axis. Good. And number 3 is a transformation on number 2. Negative 3 raised to x plus 1 plus 4. What does this do to number 2?
Up 4.
Indeed. Good, so let's graph, and then we will look at the other shape. Good, so first I am going to graph the base function. So can anyone tell us how to graph 3 to the x?
Need some values first.
Not really.
Well, it would help.
It's not a big difference between 2 to the x that we just graphed
Yeah,
and
it's
3 to
just-
the x.
Yeah, it's just instead of 2 to the power of whatever, it's 3 to the power of whatever.
Right, so just give me the shape. Is it increasing on all its domain? Is it decreasing
It's
on all?
increasing.
Increasing. And where does it
Well,
cross?
base function.
Where does it cross the y-axis? All pure, you already asked. All pure exponential functions will cross the y-axis where? Always.
0, 1.
Exactly. Perfect.
What do
So-
you mean by pure functions?
No
Functions
transformations. The base function. No transformations. Because you will see at the very end, this function will not cross at 0, 1 because of the transformations that we used on it. Good. So this is indeed 3 to the x. Then you told me to shift it to the left one, okay? So this is my marker point. I'm going to move it here. Where is this point now?
Negative 1, 1.
Negative 1, 1, I agree. So here's the graph of 3 raised to x plus 1. Then you told me to do what? You told me to,
Reflect.
good. So I'm reflecting. Where does this point, my marker is here now. Where does it go?
Negative 1, negative 1.
Exactly. So that is our negative 3 raised to x plus 1. No changes, no problems so far. What do I do now? What is the final step that I have to perform for this function? Where does it go? Up, how many? 4. So this is my marker. And this is the horizontal asymptote, y equals 0. I must shift the horizontal asymptote first. Where does the horizontal asymptote where does the horizontal asymptote go if the entire graph is shifted up 4?
Goes to y equals 4.
It goes to y equals 4. So let's say this is y equals 4. And now where will I put my marker? Where does it go?
4 spots up.
Right, 1, 2, 3, 4. So here is the final function. I do not know where it crosses the y-axis and where it crosses the x-axis. I have to investigate that, and we will when we get to solving equations. So this is the final function f of x, negative 3 raised to x plus 1 plus 4. As you see, this crosses the x-axis and the y-axis. The original function did not cross the x-axis. The original function only crossed the y-axis at 0, 1, but now this is a totally different function. Okay? Is that okay? Let's look at the other shape. Let's see what happens to f of x equals 1/3 to the x. What type of function is this? And then I have to identify what? The always. After I say to myself, this is a what type of function?
Exponential.
Exponential. Then I have to find what?
The base function.
Oh, no, we are not using transformations on this. It does not have any transformations.
Then
We just said that a minute ago. Domain. What is the domain of 1/3 raised to the x power, or the exponential function?
all real numbers.
Yes, it's a friendly function, no worries. So negative 2, negative 1, 0, 1, and 2. So let's plug in negative 2 in the function and tell me what you get. So it's 1/3 squared, but you
9.
have to flip it.
Oh, 9.
9. Then. Very good. Then.
One,
Perfect. Then.
1/3,
Very good. And then.
1/9.
Very good. So now, again, let's try to identify going this way and going this way, the end behavior. Other than Tom. 1/3, 1/9, 1/27, 1/81. Where am I going? Where am I going?
0.
Yes, 0. Which means y equals 0 is now a horizontal asymptote at infinity. Now let's go the other way. 1, 3, 81. Where am I going?
Infinity.
Thank you. Good, so let's graph the function. And we'll see it has same properties like the other one, but some of them are different, of course. Good, the first ordered pair. -2, 9, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then -1, 3. And then 0, 1, as expected. It has to cross. It's a original or base or function or no transformations are applied here. So it has to cross at 0, 1. And then I get in trouble because it's kind of difficult to plot. So this is 1/3 raised to the x. What will you say about this function? There are 8 properties here. What is its domain?
All real numbers,
What is its range?
all positive numbers,
0 to infinity. Is it increasing or decreasing?
always decreasing.
Always decreasing on all its domain. Does it have a horizontal asymptote?
At y
Yes.
equals 0.
Does it cross the x-axis?
No,
No. Does it cross the y-axis?
at 0, 1.
At 0, 1. Is it 1 to 1?
Yes.
Which means it has
An inverse.
an inverse function. Very good. So I want to graph the inverse function. Y equals x. It's a reflection of this graph with respect to y equals x. So give me a couple of ordered pairs, maybe 3, so I can remember, don't forget this. If the function crosses y equals x at some point, the inverse must cross there as well. Why? Because at this point, x and y are the same. So if you reverse them, you still get the same point. So that happens only if the function crosses y equals x. The inverse must cross at the same point. So I already have 1 point. Can anyone give me 2 more?
1, 0,
Yes, indeed, because it's 1, 0.
3, -1.
Okay, 1, 2, 3, -1. Very good, awesome. So this is F inverse. We don't know what it is yet. We will identify its domain and range right now. So let's write this. Any exponential function is defined, and I would like the domain here, and taking values in the range. So one more time, any exponential function, pure exponential function, no transformations on it, although the domain doesn't change. What is its domain?
All real numbers,
Very good. And what would be its range if it's a pure exponential function? This is not a pure exponential function. Its domain is still -infinity to infinity, but its range is -infinity to 4. So this is not a pure exponential function. But any pure exponential function will have range what?
0 to infinity.
Very good. Now, whatever this function is, we haven't defined it yet. The inverse of the exponential. We know its graph. If the function is increasing, the inverse is increasing. And if the function is decreasing, the inverse is decreasing. But can anyone figure out the domain and range? We can also look at the graph. Can we identify the domain and range for the inverse function? Exactly. So what do we say? Of course, they have to be reversed. Very good, AJ, thank you. So -infinity to infinity. So we just said that the exponential function is friendly. Why? Because the
Its
domain,
domain is all real numbers.
yes, I can sleep tight. But look at this new function that we are going to look at in a minute. The inverse of the exponential. What can you say about it? Is it a friendly function?
No.
It's not. It's not a friendly function. Look at its domain. Trouble. Like the rational has issues. Like the square root has issues. It doesn't exist if you want to apply it to anything you want. That's not possible. Very good. I would like to show you an application. So let's look on page. Let's see what do we do with these functions, with the exponential functions. Okay. Before we do that, I just want to mention one other thing is very important types of exponential functions. Why are they so important? Here's why. So when you grab your calculators, you will see there are two keys in your graphing calculator that are dedicated to two specific exponential functions. And I'll show you where they are, and you'll tell me their base. Oh, come on. It's validating something. Okay, so here it is. See this in blue in my in my software here, 10 to the x, right? And another one, e to the x. These are two very special exponential functions. So one of them is f of x equals 10 to the x, and the other one is f of x equals e to the x. One of them bears a name of common, the one with the base of 10. Yes, and the other one, you're right, natural. So this one was invented when this number was determined.
About 2.78.
Yes, 7.1. Yeah. So you're right. So this is Euler's number. Yes, it is. I think he was Swiss. Yes, it's the same. Yes, I think he was Swiss, a Swiss mathematician, and that's why it's E.
I thought it was Dutch, but okay.
I have to look it up. Okay, so it's Euler's number, and that's why the notation is E, Euler's number. Good. So both of them are of this type, or which is decreasing on all its domain, or all of this type. What do you think? Let's say we don't know what already Tom told us what it is. So let's go to second, this is right here. That's where E is, second and division. And just press enter, and you will see 2.718, blah, 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 blah.
281, 828, and it keeps repeating, right?
Yeah, no, this is an irrational number. It does not repeat any of the decimals. There is no pattern to it. It's like pi. See, it's an irrational number.
They both pass like randomness test, right?
Which test?
Like statistical randomness test. E and pi, like the
Pi
numbers that
definitely does.
Well, pi was determined in the following way.
Okay,
So
yeah,
I don't know. I have to look at what you're saying.
Sorry, okay, I'll ask you that.
So they measured a long time ago. They created circles, and they measured the circumference for this circle. Then they created this circle, and they measured the circumference. And they created this circle, and they measured the circumference and the radius. And every time they created a circle, the ratio between the circumference and the diameter, twice the radius, they always obtained the same number, which is pi. So when they divided it, the circumference of any circle on the planet, any circle that you create, by the diameter, they always got this number. Okay, so that's how pi was
Thank you.
determined. Okay, very good. So coming back here, I just want to identify what type of functions are these. Of course they are exponential, but are they increasing on all its domain or decreasing on all its domain? That's why I wanted to show you E. Both of them, 10 and E, are what type of numbers? If you say greater than 1, then it's going to be increasing on all its domain. Then if you say less than 1, then it's going to be decreasing on all its domain.
Both greater than 1.
Both greater than 1. So both functions will have this shape. 10 to the x and e to the x. Okay, so now we are ready to look at an application. Let's suppose we invest money in a bank that will compound the interest. So there are two different ways of compounding interest. One of them, so compound interest.
Monthly and yearly.
So here it is. N times per year, and the other one continuously. So n times could be semi-annually. How much is n?
6.
2. Semi-annually.
Oh.
Good. Quarterly. How much is n?
3. No, 4.
Let's say monthly. How much is n?
12.
Okay, and so on and so forth. So there are two different formulas. You don't have to memorize the formulas on the test. I'll give them to you. But we have to understand what they mean. So here's the formula. A equals P, 1 plus R divided by little n raised to n times t. The other one is A equals P e to RT. So if I'm told that the interest is compounded n times per year, I would be using the first formula. If I am told the interest is compounded continuously, then I have to use the second formula. So now let's look at one problem. Let's say 56 on page 475. Oh, 475. I have to identify what they all mean first before we look at the problem. Okay, A is the accumulated value. So P is the principal. So let's say we want to deposit a particular amount of money today, and we are really interested in how much we are going to get back X number of years later. So A is the accumulated value of the investment. P is the principal. P is the amount of money that we deposit into that bank account. R, little r, is the annual interest rate. Little n, we already know. What is the little n? The number of times the interest is compounded per year. Number of times interest is compounded per year. And t is the number of years. So time in years. Very good. So now let's look at problem 56. We are told, suppose that you have $6,000 to invest. I'm just copying the information and you'll tell me which one is which. Which investment yields the greater return over 4 years? The one with 8.25% compounded quarterly and 8.3% compounded semi-annually. I am going to add here a question not really related to this, and my question is, also find the accumulated value when the interest is compounded continuously. Well, let's say for 8.25% and for the same 4 years. Again, we are not comparing it. I just want to show you how the other formula works. So we're not trying to do anything with this to compare. Okay, So I'm given 6,000. What does 6,000 represent other than Tom? From all those 5 different variables.
Principal.
Very good, thank you very much. Okay, what does 4 years represent?
Time.
Very good. What does 8.25 represent? And I cannot use 8.25, I have to write 0.0825, 0.083. What do these represent?
The rate.
Very good. I'm going to call this R1 and I'm going to call this R2 to differentiate between those. Okay. So because we are talking about quarterly, how much is N? And then if you want N1 and N2, how much is quarterly? N1 will be
Every 3 months, and the other is every 6 months.
good. So quarterly means 4, and this is 2. Very good. So let's write the formula, plug them in, and then use the calculator because we can do this by hand. So there are 2 situations, one with N and the other one continuously. For the formula with N, I will write 6,000 in parentheses 1 plus 0.0825 over 4. And the power will be 4 times 4. I'm going to write directly 16. The other situation would be 6,000, 1 plus 0.083 divided by 2, and then 2 times 4, which is 8. For continuous, I will have A equals 6,000 times E, and the power will be 0.0825 multiplied by 4 years. Let's see what we get. Again, we cannot do this by hand. So 6,000, parentheses, 1 plus 0.0825 divided by 4, close the parenthesis caret. I like parentheses, as you already know. It's 16. So that will be the first answer. The second one, I'm just going to go in previous entry. And I just will be changing 0.0825. I'm going to put 3 and delete the rest and divide by 2, and then the power will be 8. So the next one is 8306.64. The last one for continuous, I have 6,000 and multiply by E. Here's how we plug it in. Second and E to the X right here. In parentheses, I have 0.0825, 0.0825 multiplied by 4, close the parenthesis, and press enter. So the answers, I'm going to write them down. The first one, 8317.84. The second one, 8306.64. And the last one, 8345.81. Any questions?
Raising it to a power is more powerful than dividing it, right?
Then because it's continuously compounded interest.
Okay.
Yes. Very good. So that's one application of exponential functions. Any questions from me? Any questions from me? Okay, so let's look at 4.2. I don't want to write the title just yet. We will come back and write it, put it in. So it's a different function. And we already know what this is. It's basically the inverse of an exponential function. We'll come back and fill it in. So in section 4.2, we are going to look at the inverse function of the exponential. What do we know about it? We know the two shapes. We know their graphs, right? That there are two different shapes for the inverse function. We know its domain. Can anyone refresh our memory on the domain of this new function that we are looking at, the inverse of the exponential?
I mean, it's all positive numbers.
Very good, 0 to infinity. And what will be the range? And we already established it's not a friendly function. I have to worry about it. It cannot be applied to anything I want.
Range is one of them.
And the range is all your numbers. Good, so there are two possibilities here. So this is one graph from what we just did. And this will be another. Okay. If you remember, I don't want to graph entirely your exponential function, but this was the first increasing exponential function. And we reflected it with respect to y equals x, and we got this. Then we graphed the other shape for the exponential function, which was decreasing on all its domain. And then you told me to graph this as the inverse function. So these are the two shapes for the inverse of the exponential. And I'll explain the name in a minute. What can we say? We already know. The function is defined on 0 to infinity. It has a what?
Vertical asymptote.
Vertical asymptote that x equals?
0.
Exactly. And it crosses the x-axis? Does it cross the y-axis?
No.
No. The original one, or the base function, does not. If we shift it left and right, it's going to be a different story. We'll come back to that. I just want you to give me an exponential function. Any exponential function you can think
4 to
of.
the x.
Awesome. That's a good one. 4 to the x. Okay. Now I would like you to give me 3 values of x, anything you can think of, but I would prefer one positive, one negative, and the other one 0. Because I need to illustrate something that is very important in this chapter.
Let's see.